The next section will be about real and reactive power control. When a machine is connected to an infinite bus, its speed and terminal voltage are fixed. We have ever two controllable variables, the field current and the mechanical torque on the shaft. Let's look at an alternator with a leading power factor lagging. That will be the current and the terminal voltage. IAXS cos phi. That is the induced EMF. Now if we have a constant power, that will be the loci of IA cos phi, which is this value here, IA cos phi. For a constant power, that will remain the same. If we now, let's say we have a unity power factor, which means it will be that value, then that will be IAXS, and that is the induced EMF and the load angle delta. We can now ever change to a leading power factor as well. So that the current now lies there with the leading power factor phi. IAXS is going to be that way, and the induced EMF will be there. So from this can be seen that for an overexcited alternator with a lagging power factor, E is bigger than V, and for a leading, E is less than V, and it is said to be underexcited. This machine will deliver power to the system, and this one will receive it, the power from the system. Now if we look at the reactive power, S is equal to P plus or minus JQ, and therefore P will be VIA cos phi, and Q will be VIA sin phi. Now if we look at our equation, E angle delta is V plus IAZS angle beta plus or minus phi. We can say that E angle delta minus V angle 0 divided by ZS angle beta is equal to the current IA at an angle of phi. If we break that up, we have E angle delta divided by ZS angle beta, and V angle 0 Z angle beta. Now if we draw a partial phasor diagram, we will have V there, E leading by a certain angle delta. Now if both of them is divided by beta, we will have E over Z, and this will be angle beta. The same will happen to B. That will be V over Z. Then this will be angle beta, and the angle between those two remains delta. So now if we want to determine the developed power, that has got to do with E and the current. So therefore it will be E, and if we look at our phasor diagram, at any point if we move in this direction, we start at E. The first part that we get to is E over Z, and the angle between E and E over Z is cos of beta minus V over Z, which will be cos of, let's look at another color there, that beta there plus delta. That gives us a formula of E squared over Z cos beta minus EV over Z cos beta plus delta. If we want to determine the output, that has got to do with the voltage, and therefore we have V, and then the first part that we get when we go around will be E over Z, and the angle between them will be cos beta minus delta, and minus the next part will be V over Z cos beta. And reactive power Q will be EI sin phi, where this was EI cos phi. So therefore this will become E squared over Z, sin beta minus EV over Z sin beta plus delta. And the output power Q O will be E squared, VE over Z cos beta minus delta minus V squared over Z cos beta. Now if we look at large machines, R tends to 0, and therefore beta tends to 90 degrees. Then our formulas become P developed is EV over X sin delta, as well as the output power. So therefore we can say that the losses is equal to the developed power minus the output power. And the same will go for Q. if we look at Q out, that'll be VE over X. Little. That should have been sine. Sorry. Yeah. So VE over X sine 90 minus delta minus V squared over Z sine 90. So therefore the sine of 90 minus delta becomes cos delta. So we have VE over X cos delta minus V squared over X. The next part of the work will be the loading capability of an alternator. Let's start by drawing the phasor diagram. Let's ignore the resistance, therefore that will be IA, and perpendicular to that we will have IA XS. That will be the induced EMF. Load angle, power factor angle. Now if we draw a line perpendicular to IAXS, that will be our 1 per unit power line. Now by either changing the excitation, if we make it either bigger or smaller, E changes, and if we change delta, P changes. Now let's say we increase E by 10%, then it will be that long, and now it will move on this line 1 per unit until it reaches that operating point. Delta now has become smaller, and our current has changed like that. If we now decrease E, so that E now becomes 0.9 E. E will become shorter, and now it will move up until it reaches the 1 per unit line, and we will have the operating point E2 there. Now delta has increased, and the current has changed as well to a leading power factor. Now if we look at this, this is our unity power factor line. To this side it is lagging power factor, and to that side it's a leading power factor. if we now increase our output power, that was 1 per unit. Let's say we increase it by 10%, then that will be our new power, 1.1 per unit. Now E will follow that route until it reaches that point there on 1.1 per unit, and therefore that will be our new load angle, and the current will have become leading. Now let's just have a look at an example. These problems will always be solved to scale. So you must choose a appropriate scale and then start the problem. So the first step will be to calculate our induced EMF. If we look at the exercise 2.4 number 1, where we have a 6 kilovolt 3-phase 50 Hz star connected alternator with a synchronous impedance of 0.6 plus J10, and it supplies 100 amp at unity power factor. Therefore you can calculate the induced EMF per phase which is 6000 divided by square root 3 angle 0 plus 100 0 angle 0.6 plus J10. That gives us a value. Now we are going to draw this to scale. So you choose a certain scale for your voltage so that it's not too small, well, almost half a page to a full page. So therefore there we start. That is V. Our current is unity power factor, and that will be IAZS. That is E, and again our 1 per unit line. Now, with the aid of a load diagram, determine the armature current and power factor at which the machine will operate if the power input is increased by 100% while the excitation remains constant. Now that means that our power will have doubled and the new power line will lie there. With E constant, it will rotate until it reaches that point on the graph there. So that is our new load angle. Let's say that is E1, and now our power factor angle will be measured there. Power factor angle, measure angle between E1 and IAZS. Okay. Now measure E1 E1V to scale. We divide by Z, and that gives us the current. Now the second part of the question is determine the armature current and power factor if the power remains at 200% and the excitation is increased by 1.2 per unit. So now, as E becomes longer, it will move downwards until such point that it touches the line 2 per unit, and therefore that is the case. Let's say that is E2. Again, measure the angle between E2 and IAZS. That will give us the power factor angle. Also measure E2V to scale. Divide by ZS, and that will give us the current. Now for question 3, we must determine the maximum power output. Now remember, for maximum power output, our load angle must be equal to our impedance angle. And therefore, if we butcher this picture a little bit more, this angle here is where delta is equal to beta, and then for the same current here, that is now, let's say, E3. And to get our values, do the same as in the previous steps. Thank you. Synchronizing power and torque. This comes into play when there is a disturbance on the alternator, and the synchronizing torque tends to pull the rotor back to its original position, and the synchronizing power is equal to pi over 180 times EV over XS cos delta. This is watt per electrical degree. If we want to change it to mechanical, that becomes P pi over 180 EV over XS cos delta watts per mechanical degree, where P is your number of pole pairs. The synchronizing torque is equal to the synchronizing power divided by omega S, where omega S is your synchronous speed in radians per second. If the armature resistance is not neglected, PS is equal to EV over ZS cos beta plus delta times d delta, where beta is the internal impedance angle. In the generating mode, electromagnetic power developed in watts per phase in electrical radian of rotor displacement P, EMG, is equal to E over Z cos beta minus V over Z cos beta plus delta. Sorry. Then if we differentiate it with respect to delta, we have EV over ZS sine beta plus delta. To convert it to mechanical degrees, that will be delta EV over ZS sine beta plus delta, where delta is equal to P pi over 180. Now let's look at an example. A 3,3 kilovolt 3 MVA 6-pole alternator has a reactance of 0.25 per unit. Calculate the synchronizing power and the corresponding torque. So we need to calculate P synchronize and the synchronizing torque. Now the first step, E is equal to V plus IA ZS. So therefore that will be 1 angle 0 plus 1 angle minus 36,87. The power factor in this case was 0,8 lagging. Times 0,25 at an angle of 90 degrees, which gives us 1.167 at an angle of 9.9 degrees. The synchronizing power is equal to delta VE over XS sine 90 plus delta, which gives us 3 pi over 180 times 1 times 1.167 divided by 0.25 sine of 90 plus 9.9 degrees, which gives us 0.241 per unit. To convert back to actual power, P synchronizing is P synchronizing per unit times S, which gives us 0.241 times 0.3, which is equal to 723 kilowatts. The synchronizing torque will be the synchronizing power divided by omega, which is 0.241 divided by 2 pi and 16.667, which gives us 0.0023 per unit. And again, to convert back to actual power torque, that will be 0.0023 times 3 MVA, which is 6,904 Newton meters. If we have a look at another example, which is a 1.5 MVA, 6.6 kilovolt, 4-pole star connected alternator, has a synchronous impedance of 0.5 plus J 5.5. Operating at full load, power factor of 0.8 lagging. Let's calculate the synchronous impedance. Electromagnetic power developed, and the synchronizing torque. First step is to calculate the full load current. That is S divided by square root 3 V line, which is 1500 divided by square root 3 divided by 6.6, gives us a current of 131.22 amps. The base impedance is V over I, all per phase, which is 3810.5 divided by the current, which is 131.22. It gives us a impedance of 29.04 ohms. To convert to per unit, that will be the actual divided by the base. So that will be 0.5 plus J 5.5 divided by 29.04, which gives us a value of 0.19 at an angle of 84.81. Next step is to calculate the induced EMF. E is V plus IAZS, which gives us 3810.5. Always work per phase whenever we work with three-phase work, and therefore the current is 131.22 at an angle of minus 36.87 times 0.5 plus J 5.5, which gives us a value of 4,329.57 at an angle of 7.14 degrees. The developed power, PD, is equal to E over Z times E cos beta minus V cos beta plus delta. So that gives us 4329.57 divided by 5,523 times 4329.57 cos of 84.81 minus 3810.5 cos of 84.81 plus 7,14, which gives us 408.668 kilowatts per phase, and total will be 3 times that, which is 1225.98 kilowatts. Synchronizing power, which is delta EV over Z sine beta plus delta, which is 2 pi divided by 180 times 4329.57 times 3810.5 divided by 5,523 sine of 84.81 plus 7,14, which gives us a value of 104.21 kilowatts per phase. To convert to torque, we take the synchronizing power divided by omega, which is 104.21 times 60 divided by 2 pi 1500 revs per minute, gives us a value of 1990.26. The next example that we are going to have a look at is a 3 MVA (6.6 kilovolt) 3-phase star connected 8-pole 50 Hz alternator with a synchronous reactance of 20% connected to an infinite bus. Calculate the synchronizing power and torque per mechanical degree of phase displacement at no load and at full load. For a power factor of 0,8 lagging. First step, calculate the full load current, S divided by square root 3 V line, which is 3000 divided by square root 3 divided by 6.6, which is 262.432 amps. Convert the per unit reactance to actual value, so that will be 0.2 times 3810.5 divided by the current of 262.432, which is given us a value of 2,904 ohms. At no load, E is equal to V, and delta is equal to 0. Therefore, the synchronizing power is P pi over 180 times 3 EV over XS cos delta, which is 4 times pi divided 180 times 3 times 3810,5 squared, because E is equal to V, divided by 2,904 times the cosine of 0. That gives us a value of 1,0472 megawatts. Corresponding synchronizing torque that gives us 60. 1,0472 times 10 to the power of 6 divided by 2 pi 750, which is our synchronous speed, which is determined by the number of poles. That gives us a value of 13.333 kilonewton meters. On full load, we have to calculate the induced EMF. E angle delta is V angle 0 by AXS 90 plus or minus phi. So that's 3810,5 at an angle of 0 plus 262,432 times 2.9 angle of 90 minus 36,87 gives us a value of 4,310,35 at an angle of 8,21 volts. The synchronizing power is P pi over 180, 3 times EV over XS cos of delta. Therefore, it will be 4 times pi divided by 180, 3 times 4,310.35 times 3810,5 divided by 2,9 cos of 2,1 degrees. That gives us 1.174 megawatts. Synchronizing power 60 PS over 2 pi ns, which gives us 60 times 1.174 megawatt divided by 2 pi and 750 gives us a value of 14.952 kilonewton meters. Right, that brings us to the next section, which is machines in parallel.